Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about polarization via scattering and reflection. So we're going to be talking about two more methods that light can become polarized. We have of course already mentioned the use of a Polaroid to polarize light, basically a polarization filter that preferentially transmits light along a single axis. So now we're going to be looking at techniques that involve not just transmitting the light, but instead reflecting or scattering it. You will recall from the previous discussion about Polaroids that to polarize light you have a preferential axis along which light is transmitted, or the polarization of the light is transmitted, and that this basically was because you have some long chain molecule in the polarizer which is oriented in a direction perpendicular to that axis, so that if a beam of light interacts with that molecule, that electrons are free to move in the direction perpendicular to the polarization axis, thus can accelerate perpendicularly and absorb light. And so only light that has a field that is perpendicular to that direction will be transmitted by the polarizer. We also found that the law which governs the intensity through the transmitted intensity for two crossed polarizers, or two not necessarily cross polarizers, but polarizer that is at some angle relative to the input light polarization. So here's the light input polarization, here's angle theta, and then of course the output will now be in the direction of the polarization axis. We found that the law that governed this, which is called Malice's law, is that the incident intensity times the cosine squared of the angle theta gives us the transmitted intensity. So that is what we need to remember from our last session. We're not really going to make use of either of those today because today it's more by contrast. So let's consider a molecule in the air, and let's consider a beam of light that is incident upon that molecule. Maybe the beam happens to be unpolarized, which I'm just going to represent using a pair of sort of like crossed axes. And now this beam hits the particle and scatters off. Now it can scatter off in any direction. It might scatter off this way, for example. It might scatter off this way. It might scatter off in a direction totally perpendicular to the molecule. So if these two are perpendicular to each other, what would that imply? Well, we know that the polarization direction has to be perpendicular to the light propagation direction. That's kind of in our recall. E is perpendicular to the direction of propagation S. And so down here, S is in this direction. Over here, S is in this direction. And so in order for light to have started off going this way and end up going this way, the polarization of that light has to be in a direction that's perpendicular to both of these. And the only direction that's perpendicular to both is in and out of the plane of the board. So by scattering light, if you look perpendicular to the molecule, the perpendicularly scattered polarization direction is in and out of the page towards you. So this one is polarized. This is linearly polarized. The light scattered in other directions, of course, will tend to be unpolarized, although as the angle more nearly approaches a perpendicular scattering angle, the light will more nearly approach being linearly polarized light with a direction of polarization perpendicular to this plane of the page that I've drawn. So this is basically scattering, or polarization via scattering. The other thing that we will look at is polarization via reflection. Now for this one, we don't have a nice easy explanation as we did with polarization via scattering, but the good news is that we do have a basically law or angle. The basic explanation is that anytime a wave interacts with a boundary such that some is reflected and some is transmitted across the boundary, that boundary conditions have to be met. Those boundary conditions have to do with the directions of both the E field and the B field, specifically the components perpendicular and the components parallel to the surface, or to the normal of the surface, as the case may be. There's a kind of two ways of doing it, and both are, let's say, upper division undergraduate level, so junior, senior physics, 4000 level physics course explanations. And so I'm not going to go into them in this video since it's meant for an introductory course. One of them is, again, matching electric and magnetic fields across the boundaries. The other one is similar, basically has to do with the relative direction of polarization, basically transmission and reflection coefficients. And both of them can ultimately be cast in terms of the incident and reflected and refracted angles, or in terms of the two refractive indices. Basically, from an experimental standpoint, you can take some polarizing sunglasses, basically like a Polaroid, and look through them at light scattered off of, let's say, water, like reflected off of the surface of a river or stream or lake. And you'll notice that as you rotate the glasses, the light scattered off of that one surface tends to get either brighter or darker. And so that suggests that it is, in fact, at least partially polarized. It never goes away entirely, or rarely goes away entirely, but you can get a lot of it to go away. So it's partially polarized. And basically, what happens is we have light which is incident on the surface. I'm going to actually draw that in blue. And that light that's incident in the surface can be unpolarized light. That means essentially that we expect there to be some polarization in this direction and some polarization along this direction, in and out of the page, for example. And the light that gets refracted similarly is going to have both components to it. Both a component that is in the plane of the page and a second component that is sort of normal to the plane of the page. The light that is reflected may or may not have both components to it. May or may not have both components to it. Essentially, the component which has a parallel part to the surface normal is preferentially transmitted in such a way that you can get, for some angle, light which is entirely polarized in the direction that is perpendicular to our normal to the plane. So note that this right here is poking out of the page or into the page, into the screen away from you, out of the screen towards you, and as a result is perpendicular to this. that portion, some portion of that light is always reflected. The what we might call vertical, or part that has a parallel component, is not necessarily reflected. So you may have this, so may have, and you will not have, and you will have this, assuming again some initially non-polarized light. And in some sense we might say that the light is initially non-polarized, has sort of like components of both. And I'm going to draw an exaggerated polarization like this, and then transmitted through similarly exaggerated like a large amplitude, and then here it's a relatively small, possibly zero amplitude. So this can have amplitude 0. So the condition for this amplitude being 0, so amplitude is 0, if this angle here, theta 1, satisfies the condition tangent of theta 1 is equal to n1 over n2, and this is what's called the Brewster condition. So this is theta 1 equals theta b. It's called the Brewster angle after the man who discovered it. This is of course using refractive indices of n2 for the refractive index into which the light is being transmitted, and n1 as the refractive index for the side that the light is on. As a brief example, let's consider light that's incident on the surface of water from air and figure out what the Brewster angle must be for this reflection. So basically, in water is the same thing in this case as n2. We're looking from air, so that would be n1, which as you know is about 1.00. Therefore, tangent of the Brewster angle should look like n2 over n1 is just 1.33 divided by 1.00. And since the tangent of the angle is 1.33, that means that the angle itself must be the inverse tangent of that. And so that comes out to about 53.1 degrees. That's all that I'm going to do in today's video. Hopefully you learned something from it, and as always, thanks for watching.